Okay, so let's get started with lecture 16, which is on-device training and transfer learning part 2. So remember in the last week, we talked about distributed training with a lot of GPUs, training on the cloud, how to tolerate long latency, and how to reduce the reduce networking bandwidth. In this week, we are starting to talk about transfer learning and on-device learning, right? How to enable us to learn new stuff on the edge. Okay? So from inference to training, we have this virtuous cycle, right? So many ubiquitous AI applications, and then we can generate and collect a lot of new data every day, like the self-driving car running on the road, collecting a lot of data. So it'll be great if we can utilize this newly collected data to update the model locally on the edge device, right? So be able to learn on the edge can enable customization, preserve the privacy, and enable this continuous lifelong learning, right? So this form a virtual cycle and attract more users. But we talk about training is much more expensive than inference due to the activation, due to the batch size, right? And how do we conquer those problems? So we first discussed about this code design for training, right? So first start with algorithm side and then the system side. In last lecture, we talked about these two parts. Okay? First of all, using quantization-aware scaling to enable quantized training using only 8-bit for training, right? We analyzed the difference between weight and gradient, and find that actually the quantized training due to the scaling factor, there's usually a big weight, but a very small, tiny little gradient. And therefore, we need a scaling factor to compensate for that. This is hyperparameter free and very easy to implement, just one line of code. We then talk about this sparse tensor and sparse layer update, where not all the layers are equal, right? We can selectively only update those useful layers. And even for those layers, we can do partial update. Therefore, we can save the memory and the latency and the energy. Okay, we don't have to move the entire chunk of data, but only partial data. To determine which layer to update, we also discussed this contribution analysis, right? How to decide which layer to update and which layer to keep fixed. So in today's lecture, we will talk about Tiny Training Engine. That is the implementation of all these novelties and algorithms, right? So that we can turn this theoretical saving into measured speed up and measured memory saving. So let's review about the training graph, right? So in backpropagation, we have to first obtain this forward graph, okay? In this example, we have a math mall, I have C layer, we have data, we have weight, and then we have one output. So how do we do the backward? So here we obtain this gradient, okay? And then we do the reverse direction as the forward graph and calculate two components. One is dy dx, the gradient with respect to the activation, which will be backpropagated to the previous layer. Okay? And also the dy dw, which is the weight, the gradient with respect to the weight. And finally, after we obtain these two graphs, we can give the graph to the execution engine. So conventional work, the forward graph is done at compile time. But to obtain this auto differentiation, this part is done in runtime, right? So after the model is compiled, this is actually consuming the memory and also the latency during the runtime. So can we eliminate the need to perform these tasks into runtime and offload as much workload as possible to the compile time? So here are the drawbacks for autodiff at the runtime. It has heavy dependencies and pretty large binary size, since you don't know which operator you are using. For example, if you're only using certain convolution layers, but since at compile time you don't know which one you're going to use, the binary size will be pretty large. Maybe it also includes several transformer layers, even though we are not using them at all. And the conventional training infrastructure, those operators are usually optimized for the cloud, right? For the GPU, not for the edge. Therefore, we also need customized kernels, okay, that is targeting on-device training. Conventional approach is also heavy in memory, right? There's a lot of intermediate and even unused buffers during backpropagation, which we are going to cover very soon. And conventional infra doesn't support this sparse backpropagation, right? So in last lecture, we talked about this sparse backpropagation for these convolutional neural nets, right? Not all layers are equal. Conventional wisdom is that we just update the last layer, okay, which actually hurt the accuracy. It is reducing a lot of memory, but it hurts the accuracy. And we find a good trade-off is to update only those intermediate layers, right? Remember, the intermediate layers have neither big memory for activation nor big memory for wait. Remember, for the activation, is it more heavy in the early stage or later stage for the activation? Early stage, due to the large resolution before downsampling, right? And for the wait, usually it's heavier in later stage because of the large channel number, right? So actually updating those middle layers is a good trade-off. But for existing framework, you have to calculate the whole gradient. Okay? There is no mechanism to do sparse backpropagation. Therefore, we need a customized infrastructure to support sparse update. So this is our motivation to offload a lot of runtime operation in RAD to push them to compile time, right? So this is the actual execution latency and memory we have to pay during training, right? And these are compiled, are all done at the compile time, right? So we can offload most of the workload from runtime to compile time, okay? Thus minimize the runtime overhead, and also support these opportunities for a lot of graph optimizations, which can be done since these are all static. We can perform a lot of graph optimizations, such as operator fusion and operator reordering, etc., during compile time. So here is a big picture, and let's analyze the whole training graph step by step. Okay? So starting with a Python-defined PyTorch model, okay? And we trace the static graph to obtain this forward graph. And then we calculate the derivatives at the compile time to obtain this backward graph. Okay? And we use IR, which is an intermediate representation. No matter what framework, what front end do you use, TensorFlow or PyTorch, the IR is the same. Okay? We do this graph optimization like reordering or tensor fusion to get an updated, optimized IR, intermediate representation. Okay? And then we tune the schedule. Since we already know the size of the workload, the dimension of the convolution, then we can tune the schedule for a particular device, like the tiling size, the loop ordering, etc. Right? Finally, we generate the code, the high performance code, which will be executed at training time. Okay, so a very heavy compile time operations, and very thin runtime overhead. So let's start with the first step. Okay, so starting with these Python-defined modules, and I'll give you an insight what's the difference between the Python-defined module versus this forward IR. So let's briefly look at the code. In this lecture, we have very little, as little as possible code for you to get the intuition, but sometimes we try to simplify it so it's easier to understand. So for example, this model has only one layer. Okay, so this is the input data, which is 28 by 28 by 3 channels, super small image. And the network takes in the data output of the prediction. And the net is defined by only one layer. It's a sequential layer, which is a convolution layer, right? Only one layer. Kernel size, which is three input channels and 3 output channels. So we parse that into a forward IR, okay, intermediate representation. It's telling us this is a function that has an input, which is of shape 28 by 28 by 3 input channels. Okay, and it's also telling us what is the data type. Here is floating point 32. And the weight tensor is 3 by 3 kernel, 3 input channels and 3 output channels. Okay, it's also of type floating point 32. And the operation is by performing count2D on the input with the weight. This is the dimension for the padding. This is the number of channels. This is the kernel size. Okay, so that uniquely defines this operator. Okay, and the output is defined by a percentage 0. Finally, we pass that through a ReLU function. So what's the difference between this PyTorch representation versus this forward IR? What's good about this IR versus the PyTorch module? Right, the input dimensions and all the dimensions for the kernels so that you can do the optimizations, right? So here, when we are defining the model, we don't know for this count2D, we don't know what is the size of the input, what is the size of the output, right? It has to be determined at the runtime. It gets passed with 28 by 28. Therefore, it knows that, okay, actually we have to instantiate a 2D convolution with 28 by 28 input, right? While on the other side, each tensor, we know the shape, the dimension, and also the data type at runtime, at compile time, right? Therefore, we can do all sorts of optimizations like tiling, right? We can tile the input in the XY dimension. We can do loop reordering, etc. All sorts of graph level optimizations, right? We can also fuse this ReLU into the convolution layer, right? So that's the advantage of having this forward IR at compile time. Okay. And next step is to, from this forward graph, we want to obtain this backward graph. Okay, so here the forward graph is the same as the previous slide. It's very simple. You have only one layer, which is count2D. Okay, taking input, taking the weight. These are the dimensions of the input of the weight, and this is the kernel size. Okay, and suddenly the backward IR becomes more complicated. But let's analyze them line by line. Actually, it's not complicated at all, right? So forward is the same, then count2D. Okay, input, weight, padding. These are the dimensions, right? And also we have three more sections to calculate the gradient with respect to the input, so that you can backpropagate to the previous layer, right? And the other component is the gradient with respect to the weight, and the gradient with respect to the bias. Okay? So to calculate the gradient to the input, you need a conv2D transpose. Okay? So transpose conv. Okay? With take into this original weight, and also the gradient with respect to the output. Okay? You do this transpose conv with the kernel size, etc. Okay? So this is one major component. And the second major component, you need another conv2D that takes the input and also take the grad output, the gradient with respect to the output. Okay? And then you can calculate the gradient with respect to the weight. Imagine if you are doing sparse layer update, right? This layer will, this part will be ignored since you are not updating the weight, the gradient with respect to the weight. Okay, so this is gradient to the weight. Finally, we have the gradient with respect to the bias, which is simply summing the gradient with respect to the output, and it doesn't require storing any activation. Okay, so here only gradient weight requires to store the intermediate activation. Okay? Calculating the bias doesn't require that. Calculating the gradient with respect to the input doesn't require storing the intermediate activation either. Okay? So as a very rough estimation, if forward takes 10 milliseconds, how long will it take on the same device for the backward? Considering forward, right, and gradient input, and also gradient to the weight. So we have 3 convolutions for the entire forward and backward, compared with only 1 convolution for forward. So it's 3 times, roughly 3 times longer with respect to the latency, right? Okay, so let's go to the major part, the most exciting part, how to support this sparse layer and sparse tensor update. So we already obtained this IR, the intermediate representation for training, right? We get both the forward graph and also the backward graph, and also we know the dimensions of all the tensors. Okay, it's no longer dynamic, but it's static. It's already known at compile time, so that we can determine what is the dimension we are going to update and what is going to be kept fixed. So imagine this is the 3 or 4 scenarios. I will describe one by one. Okay. So the first scenario is the full update. I'm going to update all the layers, the weight, also the bias. Okay. Second one is only update the bias. Third one is sparse layer update, not updating this one, only updating this one. Fourth one is sparse tensor update. Okay. Only update partial of the tensor. Okay. So given this forward equation, so y equal to xw times plus b, the backward dy dx, okay, equals to the previous gradient times the w. Okay, so dy dw equal to the g transpose times x, okay, and dy db is just summing the g together. So this is the mathematical representation. I believe there should be a transpose here, which is a typo. We can fix that later. There should be a transpose. So this is the forward graph, right? So for the backward graph, during the full update, we have to calculate all these components, multiplying one multiplier, one transpose, another multiply, another sum, okay, to calculate dy dx, dy dw, and also dy db. What if we have this bias only update, right? So in bias only update, which line can we eliminate in this case? So we are only getting dy db. We don't need to. Which one can we eliminate? Yes, the dy dw one, right? Since we are not calculating the gradient with respect to the weight, therefore we can remove the code to calculate dy dw, and the transpose operation can also be eliminated. What about if we do sparse layer update, right? So here we have a flag called need grad for the weight, for the bias, weight and bias, right? So if a layer doesn't need to be updated, then we can set a flag that need grad to be false for both scenarios. What about sparse tensor update? So here, originally we have to calculate the gradient with respect to the weight and also the full weight, right? But currently, for example, here we only update half of the weight. So what do we do here? We give needs grad to be 0.5. So here we can chop only half of the tensors. Okay? The dimension is only 10 by 10 rather than 20 by 10. Okay? Only half of the total height, right? So here we can do the multiplication on the new tensor, which is of dimension 10 by 10 rather than originally 20 by 10. Therefore, we save half of the computation in this scenario. So these are the advantages of manipulating the graph at compile time. Okay? So you know all the dimensions, you know all the tensor, you know all the data types. Therefore, you can feel free to have your own scheme among these four schemes, right? Either bias only, or sparse layer update, or sparse tensor update. Actually, this method is quite effective if we compare the peak memory consumption compared with a full update, where you have to do back propagation all the way to layer 1. On the microcontroller on different workload, it can reduce the memory from thousands of kilobytes to only hundreds of kilobytes, right? So ranges from 6.5x reduction to 8.7x reduction just by this sparse update, right? So this is the example on image classification tasks, right? So we also explored such techniques on transformers running on BERT. And the similar rule, similar method can also save the memory consumption on the language tasks like BERT. Okay, all right. So what are the other opportunities we can do on the intermediate representation? We can also perform operator reordering and in-place update. Okay? So we have seen this figure before during the distributed training section, right? So this F stands for forward, B stands for backward, and U stands for update, right? So conventional way to update the parameters, we calculate different layers, layer 0, 1, 2, 3, and then we calculate the backward, get the gradient for layer 3, gradient for layer 2, layer 1, layer 0. And then we update layer 0, layer 1, layer 2, layer 3, right? So we form this zigzag pattern, right? Is this optimal? Are there opportunities to reduce the life cycle of the tensors? So here we have this big, pretty long cycle between the producer and the consumer, right? So we spend a lot of time. This tensor, the gradient tensor, has to be stored in the memory before it is consumed, right? What about we just immediately consume this tensor as soon as the gradient is calculated, which is the second part, right? So we can immediately do the update as soon as the backward is done. For that layer is done. For the second layer, it's not complete, it's not started yet, but it doesn't hurt us, doesn't prevent us from updating layer 3, because the gradient for layer 3 is already computed here. So we can immediately do the update and release the space, right? So we can free this memory space and continue to do the layer 2, right? After calculating the gradient of layer 2, we immediately release the buffer and update the weight, right? So we do that for layer 1 and layer 0 in a similar fashion. Question?
Why don't we just always do it that way? Why don't we just always do it that way if it's better?
So this is like what TensorFlow and PyTorch is currently doing, right? The drawback here is you have to manipulate the update the weight, and also to maintain the relationship between the whole schedule. So that's the conventional way you update. You calculate the forward and then you calculate the backward, right? And after computing the whole backward, like step 1, 2, 3, and then you do the update all at once, right? So this is very simple to write the code. If we do the conventional way, we calculate the loss, okay, and we calculate the gradient, and we update the gradient, right? So very simple code, but not efficient. Versus if we we do a simple for loop, and for layers in the model, we calculate the backward with respect to a particular layer, and then we immediately update that layer, okay? And then we calculate the loss for the previous layer, and then we continue this process by putting loss here. Okay? It will do the other way, where we do forward 1, 2, and then gradient for the layer 3, and then we immediately do the update. And then we calculate the gradient for this layer and do the update, and etc. Right? So in this way, the control logic is a little bit complicated, but not rocket science. But this greatly simplified the buffer and make it more memory efficient. Actually, this method can save the memory from 500 kilobytes to only 160 kilobytes, okay, by such simple reordering techniques. So these are 3 different models: a bigger one, a middle one, and a smaller one, right? So by such reordering and in-place update, we can drastically reduce the peak memory. So actually, there's a lot of low-hanging fruit using such seems very simple techniques compared with the existing PyTorch and TensorFlow methods. Question?
So you cannot change. So, for example, when we're running a code to one GPU, can we manipulate the PyTorch to do it this way? Because it's like saving 3 times memory.
So a caveat here is that we are running on just a couple of kilobytes,
Yeah,
right?
yeah.
But the main bottleneck when you have a batch size that is consumed by your activation size, which is not, here we are just using batch 1 of training, right? So therefore, in the tiny scenario, this kind of reordering, this kind of memory for the gradient matters. But when you are training large-scale language models where the activation matters, the activation will dominate. And this method will not save the memory for activation, only save the memory for the gradient. Yeah. All right. So here we did some further analysis by running this operator's life cycle analysis. So what is life cycle analysis? To see each buffer, what is the start time and the end time for the buffer, right? So this is the total number of cycles. This is the life cycle in the x-axis. We can see after the optimization, all the operators can finish at about 200 cycles versus 240 cycles, right? And the y-axis is showing the size of the total number of buffers. Okay, so the weight have to reside in the memory the entire time, right? So these yellow parts are for inference. Okay, so inference started at cycle 0, finished around cycle 60 or 80, right? So a majority of the memory is consumed at training time by the activation, by the gradients, okay, and also the activations. So by using such operator fusion, we can reduce the memory consumption by this tensor. Okay, so actually we are fusing the tidying and reshape operators together with those convolution layers. Okay, so we fuse them into a single operation. We can also do such in-place gradient update so that we can avoid having such long cycle and long memory of storing those gradients, since we are applying the update immediately after we calculate the gradient. And as a result, we can shorten the total training time and also greatly lower the total memory footprint. Okay, so having optimized the IR, remember we talked about this operator reordering, we talked about this sparse update. Now we can obtain a graph. We know all the dimensions, we removed all the redundant computations. Finally, we can tune the schedule. Okay? Tune the schedule means we fine-tune the blocking size, the loop orders, etc., given a particular hardware platform. So existing operators like TensorFlow Lite are optimized for this mobile mobile CPUs, but on microcontrollers that require a totally different scheduling. Okay, so this is the performance after tuning. Okay, we find such optimized operator can make it 23 to 25 times faster than the original TensorFlow Lite Micro on the MCU. Okay, so we require only a couple of hundred milliseconds. Okay, only a couple of hundred milliseconds to do the forward and backward. For example, running MCUNet, you can roughly process 2 images per second. Okay, finally, this is the last part. We can generate the binary by only compiling those operators that is used in the graph. For other operators, if you didn't use any 5x5 kernel, we don't have to compile them at all, right? So we can deliver a very lightweighted, portable, and efficient binary. On the microcontroller, we have only about 1 megabyte of flash. That's a very small amount of resource. So even the binary size matters. So it's very crucial to have a very lightweighted memory footprint for the binary size. Okay, so this is another comparison about conventional training frameworks, okay, that performs most of the tasks at runtime, which is in red. A lot of workload is runtime, including the auto diff and run. But Tiny Training Engine separate the runtime and the compile time and the runtime. Okay, we are pushing a lot of workload during the compile time, okay, including sparse update, fusion, and reordering, so that we can finally generate a code that's very lightweighted. So with the same accuracy, this is the memory saving, this is the acceleration result. So quite effective, 20x smaller memory and 23x faster speed. And here we have a demo here showing the effectiveness of tiny on-device training. We have 2 buttons on the microcontroller, which is the same one you will be using for Lab 4. Hopefully you already picked up one of these STM microcontrollers. 2 classes, therefore we have 2 buttons. We click the button to give it a label, right? We can point it to another thing to give another label for the orange. Now we no longer need any inputs, any labels, and can automatically differentiate different classes. But the headache here is that you have to have these buttons to provide the input, right? So can we have unsupervised or even self-supervised learning? So in the our recent work, we also explored fine-tuning these language models. Right? For example, in the iPhone, we can train our own text by analyzing the emails, right? Therefore, we can actually customize the language model for different users. And we find such sparse update technique can also apply for the self-supervised scenario to train those language models. This is another demo we have seen before. It can run about 1.8 frames per second on a microcontroller. Feel free to use this. We can give you the source code if you want to work on your final project based on similar techniques. Okay, so after a couple of epochs of training, we can run the new task, which is detecting person versus no person. Detecting person is quite important in a lot of IoT applications for smart home. Like you can trigger the music, trigger the camera to record the room only when you are seeing a person. Right? Previously, people use this kind of motion trigger, but even the falling leaf can trigger the video to be recorded, which is not accurate. But using such technique, you can accurately determine whether there is person or no person in the scene. So for such tiny on-device training technique, we can match the TinyML perf benchmarks accuracy by purely training on the edge. Okay, so far we talked about on-device training on very extremely memory-constrained devices like microcontrollers, right? So we want to expand the application scenario beyond microcontroller to other edge devices, right? And also we want to expand it beyond convnets to also transformers, like we mentioned. So diverse models, diverse applications, ranging from convnets to transformers, which is a hot topic recently, and also diverse front ends, including PyTorch, TensorFlow, and also JAX, which is very popular recently. And also we want to support diverse backends, okay, ranging from Android phones, Raspberry Pis, Apple M1, Qualcomm Snapdragon SoC, and other edge devices, right? So Tiny Training Engine provide a very versatile bridge between diverse models, diverse front ends, and also diverse hardware platforms. Okay? And the idea is very similar: auto differentiation at compile time, prune the graph to remove those redundant operators for sparse backpropagation, fusion, and reordering to save the gradient memory. And we also did another other functional preserving optimizations. For example, the Winograd convolution, which we will cover in the next lecture. So conventionally, Winograd convolution is only used in inference because the weight has to be constant, right? But for training, conventional update will change the weight. Therefore, we cannot calculate the Winograd transformation very easily. But with sparse update, we can actually do the forward for those fixed non-updated weight in the Winograd format, which can accelerate the inference and also accelerate both forward and also accelerate the forward and backward stage because the weight, some of the weights are fixed. And Tiny Training Engine is showing quite good result on Raspberry Pi. For example, you can actually do about 10 images per second for MCUNet, about 9.5 frames per second for MobileNavi2. Okay, so the total latency of running a forward and backward using 224 by 224 resolution is only 100 milliseconds on a small Raspberry Pi. And the forward itself is about 30 milliseconds, which is pretty exciting. You can do a lot of stuff using the Raspberry Pi. If you need one of those devices like Raspberry Pi, feel free to talk to us if you want to use it for final project. Even for BERT, right, we can perform about 3 to 4 sentences per second. Even for DistillBERT, can roughly process 7 sentences per second on a tiny Raspberry Pi to train the fine-tune the language model. Okay, and here if we compare the red one versus this blue bars, we can find actually the full beat backpropagation versus the sparse backpropagation, where the sparse backpropagation can have quite significant improvement with respect to the latency, right? From 6 frames per second to about 9 frames per second. So here we can use it for diverse hardware platforms. It's very likely if you want to do your final project, you can either use a mobile phone. Okay? Here we use the Qualcomm Snapdragon 8 Gen 1 SoC, or you use the NVIDIA's Jetson Nano mobile GPU, okay? Or you can use cheaper Raspberry Pi 4B Plus. Okay? And this is showing what we can do on these devices. So on the CPU, this is the dense update versus the sparse update. This part is the gray part is the forward part, and the red part is the backward, right? So without optimization, it's roughly taking 180 milliseconds to process the forward and backward for one image. Using sparse updates, it can take only 90 milliseconds. It can run roughly 10 frames per second to train 10 images per second on the S8 Gen 1 CPU with MobileNavi2. Okay, so on the DSP, so this SoC has a CPU DSP and also GPU, right? So DSP is much more faster. For example, with MobileNet V2, it takes only 1 millisecond in our experiment to run the forward and backward for one 24 by 24 image. Although currently there's one more bottleneck since the infrastructure doesn't allow this update. So we can calculate the gradient, but we cannot do the gradient update, which is not is a very low hanging fruit, but we haven't solved it so far. But if that is solved, it's super promising to train to do on-device training. 1,000 images per second on the DSP. Currently, it's about 10 frames per second on the CPU. So on the Jetson Nano, it's requiring only about 5-6 milliseconds to train one image. So it's very likely you do your homework, do your final project by using Jetson Nano to try some new ideas, right? Build some applications. On Raspberry Pi is similar, about 90 milliseconds to the forward and backward. And sparse update is consistently showing the benefit about 1.7 to 1.9x speed up for training on device. Some highlights on the MIT News, where it's a cool technique enable AI models to continually learn from new data on intelligent edge devices like smartphones and sensors, reducing the energy costs, privacy risks, makes deep learning more accessible. All right, so this is a summary of the take-home for on-device training, where there are 3 components, right? Quantization, sparse update, and system support, tiny training engine. On the quantization part, we mentioned the fake quantization has to keep the FP32 counterpart in the memory, right? It is designed for a quantization-aware fine-tuning, but not designed for quantized training. Okay? Quantization-aware fine-tuning is targeting inference, okay? Training the quantized graph for inference. But at inference time, you don't have access to any floating point units on, say, some low-end device, right? Thus, such fake quantization isn't possible. But quantized training on a real quantized graph is difficult. The difficulty is actually coming from the mismatch between the weight and gradient for the gradient for the weight and bias, right, due to the scaling factor. So with quantization-aware scaling, which is very simple, no hyperparameter tuning, just 1 or 2 lines of code, you can actually make it converge. Okay, make quantized, directly optimize those quantized graph. So sparse learning, okay? So sparse learning happens in human brain, right, from 2 to 4 years old to adolescent. Similarly for artificial neural nets, we can update only those important layers and only do partial update. But we need system support in order to convert, to realize such theoretical saving into measured speed up and measured memory saving. So we are going to use this technique where we are going to calculate the gradient at compile time, okay, autodiff at compile time to minimize the runtime overhead, okay, and use tiny training engine to fit the overall training on a microcontroller. So when we talk about a lot about on-device training, so is it safe to perform on-device training? Since we are exchanging the gradients, we are exchanging the models, we are not exchanging the data, does that prevent us from actually leaking the raw data? And we are going to show several techniques try to leak the raw training data from the gradient, which is very interesting. Okay, so this motivation for on-device training, which is the same as before, right? We motivate for customization, say people may have different accents, right? But also security is very important. The data shouldn't leave the device, especially for sensitive data like in hospitals or where there are regulations. So this is the background for federated learning. Why do we need federated learning where different devices are using its own local data to update its own model, and they only exchange the model update rather than exchanging the training data. And the reason is because of the privacy of the data, right? The data is everywhere. You want to fully utilize different sensors, different devices to collect them, but they are usually isolated due to the privacy issue or due to regulation issue. So federated learning provides a way to utilize all of this decentralized data without having to centralize them, like we discussed in the last week's lecture. So this is the popular fed average algorithm, which is widely used for input methods. Right? So different people may have different vocabulary, different contexts. Right? So when you are typing something, it's try to learn a customized model for your habit. Right? So it starts with a user, with a model, and with some data to update the model. So this is the updated model from a particular user, right? And you may have multiple such users represented by multiple phones here. So they initially get the same model from Apple Store, for example. Okay? After a while, each of them may have completely different models, since different users may have different data, different habits, right? So they exchange the model rather than exchange the data. So finally, we have a new model, okay, which will be aggregated and disseminated, which will be aggregated and then disseminated and averaged on the server and sent back to different devices. So this private user data never leaves these edge devices. So they're actually averaging the model rather than averaging or exchanging the data. But does this really protect the user information? So we want to rethink the safety of gradients since we are exchanging them. So convolutional neural nets given to different images, we can have different predictions, and we can derive gradients from model and training data to get the gradient, which is the normal training process. So given, we try to answer the question, given the gradient, okay, does the gradient contain the information of the raw training data? Intuition tells us it does because gradient is calculated by using the inputs, right? Therefore, it must be containing some of the information from these inputs. And the question here is whether we can recover the input image by using these gradients. Let's brainstorm for 1 minute to think about this question. Can we try to steal, to recover, to leak the input image by observing the gradients?
Are we assuming that the adversary can input anything they want into this black box and they get to see the gradient as the output?
Yeah, you can imagine you can give any input to the system.
Okay.
Emma.
You could probably reconstruct the image really gradients because you would, if you use like an autoencoder structure, I feel like you'd be able to recreate the images.
If you have an autoencoder structure, the autoencoder's input is the input image, but now you only have the gradient. So what's the input for the autoencoder?
Somehow the gradient.
Somehow the gradient.
The array of the photo. I don't know how, but I'm convinced it could happen.
Yeah, intuitively, that autoencoder can recover the input image, but this is the gradient, actually not the input, not the image. Right?
I think the question should be reversed. Prove that you cannot predict the data using the gradient. Not prove that you can. Prove that you cannot.
Actually, we can do that, but here the question is, how can we do that? I'm going to show you the result very soon, but hopefully we can do some brainstorm to see, given this gradient, how to recover the input.
I guess if the adversary knows which classes I'm looking for, and the adversary has their own cats, dogs, etc., can they just feed those in, get a set of gradients out, and then do some sort of k-nearest neighbors or some other try to match the gradient that they observed somehow to the set that they generated to see where it maps to closest?
Yeah, very close. You mentioned match the gradient, right? So we can generate some random input, random labels, and try to match. We can obtain a gradient and try to match the gradient with the original input's gradient. And then we can do backpropagation to optimize the fake, the adversarial input and the label. That's exactly the method. So let's see how that happens. Okay, so before that, let's see some weaker solution where we try to find whether a data point belongs to the batch, right? So this is a weaker way of try to steal the input data from the gradient. And it's showing that actually we can get whether an input belongs to the training data or it doesn't belong to the training data. We can even find whether a data point with certain property is in the training data. Say whether someone wearing a gray suit is in the training data, then it can tell you whether that is in the training data. But both these methods is kind of weak because it only tell you whether some data point exists or some certain property exists. It cannot steal the raw data. So these are called membership inference or property inference. So since gradient contains so much information about the training data, can we just obtain the raw training data, the raw image from these gradients? Actually, this is exactly the method. So given a normal participant, and here we have a malicious attacker, given the original cat image, given we pass it through this differentiable model, okay, with weight W, get a prediction. At the same time, we get a loss so that we can calculate the gradient with respect to the weight, right? Since we have the ground truth label, we can calculate the loss. Therefore, we can calculate the gradient. So this is the normal participant. And there's a malicious attacker, right? So the attacker initialize a random input. This is just random input. And this is a random output, random label. Okay? So what it's going to do is basically pass through this this input image into the same model, okay, with the same W, okay, and get a prediction slash, right? So this is the attacker's prediction given this random input. Using the prediction and the random output, we can calculate a loss with respect to the weight, right? And here we are trying to match the loss and trying to match the gradient to make this gradient to be the same as the original normal participant's gradient, right? So here we can try to match these two gradients by calculating the difference of these two delta W. And then we backpropagate this loss to update the input and also update the random output, right? By trying to match these two gradients, so we can calculate the loss, right? We can use this loss to backpropagate to the input and backpropagate to the output. Okay, so we can tune the input, and after a couple of iterations, we can actually recover the image. So let's see that in the code in a concrete manner. We initialize the input to be random noise, okay, random noise. We also initialize the output to be random noise. Okay? And after that, we try to calculate the loss, okay, using this input, using this output. Okay? We try to calculate the loss, therefore the gradient with respect to the weight, using the dummy input and dummy output. After that, we calculate the distance between the normal participant and malicious attacker's gradient. Okay, we calculate the loss, and then we can update the dummy input and also the dummy output using this loss and try to minimize the loss by tweaking the dummy output and the dummy input. And after a couple of such iterations, okay, we can recover the input. So this is the effect. Okay, so this is our TAs, right? This is me. So we have initial random initialization, right? So this is the recovered image. This is the ground truth image, right? So initially, the recovered image is purely noise, but after a couple of iterations, it's going to recover the input image.
How many forward passes does this take? Just order of magnitude? Is this like on the order of 10, 100? Like, yeah.
Yeah, so on the order of 10, right? So this is another example, right? Iteration 0, 10, 20, 30 iterations. So initially, we initialize something with a purely random noise, purely noise sentence. Okay, this is the original text we get from the New RIPS website. Registration, volunteer application, and student travel application open the first week of September. Childcare will be available. Right? We try to attack by stealing the raw input sentence, first initializing a random input, and to backpropagate, try to match the gradient. Okay, since we can obtain the gradient, we try to match the gradient. Iteration 10, iteration 20 is already almost there, and after 30 iterations, I can actually recover the full sentence. What is assuming here? This is assuming we can obtain both the weight and the gradient, right? Say if you have a mobile app on Apple Store, you do have the weight, right? And if you exchange the gradient, it is also possible to get others' gradient. So be careful about your gradient, not only the data. What about some defense strategy? Is there a way to prevent such leakage of the gradient, of the data from gradient? Let's brainstorm a little bit. This is adding noise. Let me start with something that doesn't work, and then I'll give you time to think about something may work.
One of the major assumptions here is that the model is deterministic. Like every time you put an input, you're going to get put in the same input twice, you get the same gradient twice.
Right.
But could you make the model non-deterministic?
Very good point. You can actually use the once-for-all network. At different time, you are sampling a different subnetwork, right? And you don't know, the attacker may not know which subnetwork you are actually using. Therefore, you do have the full weight, but you don't know which partial weight you are using. So in that case, what are we trying to break? We are trying to break the W, right? Here, the W here, and W. The W for the participant, normal participant, versus the W for the malicious attacker are actually assuming they have the same weight. But if they don't have the same weight, it might be possible to prevent that. But that might require some experiments. So just a direction. I haven't done that, so I cannot say 100%, but that's a good direction.
Use a larger batch size. I know you've mentioned in previous paper you can still infer if a specific shade is in the batch size, but it seems intuitive that if we have a larger batch size, you cannot infer.
Right, that's another good point. If you increase the batch size, right, it's like you're solving an equation. There are so many parameters to solve, but there are just limited number of functions available, right? We are trying to match the gradient, which is a fixed number of dimensions in the gradient, right? What if we have a super big chunk of images, so many pixels? And to calculate each pixel will be harder and harder. Like if you have only 2 equations, but you are trying to solve 2 variables, that's doable. But if you're increasing the lot batch size, that is equal to if you're having 2 equations, but you're trying to solve like 10 variables, then suddenly it becomes very difficult. So definitely that's another way to prevent such attack. Very good point. So let's see some intuitive method, but actually it doesn't work. Adding noise, right? We can add noise, go original model, add some noise, adding more noise. Okay. Actually, after adding the noise, for example, adding 10 to the minus 3, after a couple of iterations, this is the gradient match loss. We can still leak, but with some artifact, right? So when we are not leaking the information, actually the accuracy is actually getting pretty bad. So neither Gaussian or Laplacian noise can defend the leakage unless we can tolerate serious accuracy drop. What about using quantization, like half precision? Even by using a P16, we can still observe deep leakage. We can recover the input image like a tree. Similarly, this is for using pruning, right? So actually pruning is a way to solve this method. And why pruning can, gradient pruning, why gradient compression can effectively protect the privacy leakage, and why do we need sparsity ratio to be larger than a certain number. So here we are showing the gradient match loss with the original model, and this is pruning 1%, right? Still deep leakage. Prune about 20%, it will leak with some artifact. If we prune more, like this purple line, prune 70%, is not going to leak the information. And the reason is that if we are pruning the gradient, when we are trying to match the gradient, it's like you have less equations, less matches, right? But you have the same amount of parameters to solve. So you have less clue what to match, right? You're trying to match the gradient, but suddenly most of the gradient, more than 30% of the gradient are pruned. So therefore, you have less clue. Okay? It's like you are sending less information to the malicious attacker. Right? Therefore, it's less likely to attack that. And another limitation is that you see all the images are pretty low resolution. Right? For example, in this demo, the resolution are all pretty low. We find it harder and harder to attack high resolution images. And why is that the case?
Increases at higher pace than the number of gradients.
Right. The number of gradient is fixed, right? If you have a larger input resolution versus smaller resolution, the gradient size is always equal to model size, which is irrelevant of the resolution, right? But if you have a larger input resolution, you need to attack more pixels, right? You have to calculate more pixels, but you have the same number of equations, which is equal to the number of the size of the gradient, right? Therefore, it's hard to leak a lot of information with a large resolution using the same amount of input information, which is the number of gradients. So that's similar reason why it's harder to attack a larger batch size. So compared with, it's harder to attack with a larger resolution. Right? Okay, so hopefully that provides an interesting perspective to rethink the safety of gradients, rethink the safety of exchanging gradients, exchanging model updates. All right, so this is a summary for this week. Okay, we talk about system co-design for on-device training, including quantization, and also sparse update, and also the system support. We also introduced in later part of this lecture why federated learning is because of data. Right? Data never leave the device and only exchange the gradient and models. Right? Allows jointly training without exchanging data. But we want to rethink the safety of this paradigm by examining the possibility of attacking leaking the input image by examining the gradient. Right? Conventional wisdom is showing that we can only leak those high-level information like membership or certain properties, but deep leakage from gradient, our NeurIPS 19 paper is showing it's actually possible to leak the full image and also the text from the gradient. And a very effective way to prevent such leakage is by using gradient compression and gradient pruning. Okay, so hopefully this lecture is helpful for your final projects, giving you more opportunities and to do more interesting project, not only inference but also training. All the devices we described in the lecture, we have them available in the lab. So if you need those devices, feel free to contact us, and we are happy to help you to brainstorm exciting ideas. Okay. So next lecture, we'll continue to talk about TinyEngine, which will be used in our lab 4. So I hope you can all come to the next lecture. Thank you.